Hi, this is Yashan Mohan Kumar. For this continuous assessment, I took the hotel booking data set.
And my name is Karthik. I took a ride sharing dynamic pricing dataset.
This is the topic of our things that we took. This is risk sensitive, which is basically on dynamic pricing, and this is the cross study of like hotels and ride sharing revenue management, which is based fully on optimization techniques. And second, I will dive into the problem that we are facing under certain uncertainty. And pricing is genuinely hard for any service, businesses. Too high and customers leave too low and you lose money. Demands keep changing every time. So with season on time and how busy the things are. Most reinforcement learning pricing works only when optimization average revenue becomes higher. And so the challenge that we face is like now I said the prices are too high, and if a customer books, they might cancel later. So that's the biggest challenge ever that we face. And our angle here is like mostly on reinforcement learning pricing, which maximizes the average revenue only. But a policy that we have made to like V2V creates a cash flow risk, like J is equal to E of G minus lambda into variance of G. So this is the technique of our formula that we use for this. So for us, the two questions that raise when working on these data sets were, does reinforcement learning optimizes and produces a high sort of certainty for giving a high profit, but simple pricing rules manages the risk equally. So now let me explain the MDP setup. So this is the Markov distribution process, and this is like when the agent observes a state and picks up a price like this. Each agent acts with an environment, and so for my data set, I have took like around 160 states. Like each state has an parameter like lead time, season, market segment, and an occupancy. Karthik's right share state has 48 locations and time of day, vehicle type, and a search flag. So the action is one of the five price multipliers from 0.80 to 1.25. So the reward is price paid minus a penalty for the risky secondary ones. Gradient boosted classifiers to simulate demand. The agent interact with the simulator simultaneously. The same MDP structure across both datasets is what makes a comparison meaningful. Now the two methods are shown to you in the next slide. The first slide, our approach implemented two methods on our dataset. The different datas we used, like one is the hotel booking dataset and another is the ride mean sharing. Here, the mean variance Q learning uses a tabular Q learning plus a second table that tracks each variance one by one. And the second movement, we can compute variance where the agent picks every steps or episodes that it considers. And the second is the Bayesian network, which is a seven node sort of hill climb search. And this is a genetic algorithm. Like policy vectors, scoring each by networks expected a reward a slower variance. Both are compared against the three baselines, fixed price, peak of peak, and evaluation like for around 200 paired episodes, with match seeds of random value 42, which is the most sequentially followed value. Now I'll show my hotel results, what the dataset generated. So this is what the bar chart that my dataset gave as an output. And here the three Q learning agents on the right beat everything else. Is lambda like around 0.005 with a mean like of around 1871 as the standard episode. That's over 97 and the fixed sort of price. At zero point zero 0.01, the standard deviation dropped 9%, which is like less number of um, uh, calculation amount. The Q table noise is very noisy, so pure greedy policy over exploits the situation. The noise with high variance entries pulls the agents away from those which act as a regularizer. Neither the baselines nor the B and GA significantly beat fixed price on hotel data. Q learning was the only method that did. Handing over next to Karthik.
Thanks, Yashwant. From here, I will cover the rest. Here, these are the right share results which has been done by me. The pattern is very different from hotels. My right share data has 1,000 trips with rider and driver counts, location, time, vehicle type, and price. My state is location, time of booking, vehicle type, and a circ flag. When riders outnumber drivers, that gives 48 states. The long ride AUC on my demand model, like area under curve on my demand model, is 0.97. So the demand signal is very clean and easy to predict. The greedy regression baseline wins outright at 14,820 per episode, more than 2,000 above fixed price. Statistically very significant. Q learning still beats fixed price at lambda is equal to 0. So it is robust, but it is not the best method here. And on this data set, increasing lambda reduces the mean, the opposite of what Yashwant saw on hotels. The reason when the demand signal is this clean, there is almost no estimation noise for variance penalty to smooth out. So the myopic optimizer wins. That contrast between hotels and rideshare is the crux of our team finding, which I will show next. This is the cross data set comparison. Looking at both data sets side by side, four things came out. One, Q learning is robust across both domains. It always beat fixed price, never harmful, a reliable default. Two, our main finding is the best method depends on how noisy the demand signal is. The noisy signal on hotels, apart from that, Q learning wins here. Clean signal on my ride share data, the greedy wins here. That is the rule of thumb across the two domains. 3. Risk aversion pays off when the data is noisy on hotels. Turning the lambda up improved both the mean and the downside. On my clean right share data, the same tuning hurt the mean. 4. The simple handcrafted rules like peak off in both domains, no naive rule generalizes. That is the argument for a method that learns from data. A quick live demo at the code, I will show it for you. This is the part which has been done by Yashwant. On the left is a sample of the pipeline output. This is Yashwant's hotel run. Uh, yeah, mine is looks the same with the right share numbers. Everything is reproducible with 42 seed runs in about a minute on a CPU. On the right, there are five things the demo covers: folder structure, demand, pipeline running, and run experiments.py, opening the results folder, checking a figure matches the report, and running py test. All 9 tests pass on both code bases. Both my right share code and Yashwant's hotel code share the same modular structure, which is made adapting the methods across the datasets clean. This is the snapshot of the results that we have done. And the next thing is the distribution of work in between us. On the split of work, Yashwant did the hotel booking, demand study end to end, the shared MDP setup, the Q learning, and BNGA code, the hotel demand model, the three baselines, the evaluation, and the stats, and the shared code architecture that both studies reuse. I did the right share study end to end, like data preparations, state designs, adapting both methods to right share, the demand model, figures, unit test, and reproducibility checks on both code bases. And finally, the core concept or else the outcome that we had learned from the project is the key takeaways that has been described here, like risk sensitive q learning beat baselines in both domains. Risk aversion also acts as a regulator against noisy value estimates. The best method depends on how clean the demand signal is. So thank you, thanks for watching. We are happy to take any questions.